All right, so we're just going to jump in and get started. So here we have a structure known as isoleucine. So it's one of the amino acids that your body produces naturally. And the first task that we need to do is ID all chiral centers. So remember our criteria for chiral centers. We're looking for these sp3 carbon centers with 4 different substituents, 4 different subs. And that was like the thing. So we see that we have, a great indicator, is that wedge dash like structure. But, we can verify that by, if I circle that carbon, I see that I have this ethyl group to my left, this methyl group on a wedge, this hydrogen on a dash, and then this whole right fragment to the right. So it would be 4 different substituents at that sp3 center. So that is definitely a chiral center. Over here, we see we have an amino group, that carboxyl group, this whole left, whatever alkyl group, and then this dashed hydrogen group. So that's 4 different groups. So those would be the 2, chiral centers in this entire, amino acid. The second thing is to assign absolute configuration. So if we're considering, this first chiral center all the way to the left, we're basically going to see that, the right side of this molecule is way, way more complicated than the left side. So I would think in terms of labeling priority, I would say to the right is 1, my left is 2, and up is 3. And that hydrogen is definitely the 4th one. It is oriented away. So tracing that is clockwise, and that would be R. Okay. So if I were to look at this other one on the right, the amino group has a nitrogen, so that's clearly number 1. This carboxylate group is clearly more, has oxygen atoms than this carbon fragment to the left. That's 2. And then the left would be 3. And then hydrogens are already 4. So if I were to trace that, that would be counterclockwise, and that would be an S configuration. All right. So then the last part would be C, draw the enantiomer. So if I were to draw the enantiomer for this, it would be the structure where every single, chiral center inverts its configuration. And the way I know how to invert configuration is to just simply put the wedges as dashes and the dashes as wedges. So that would be the enantiomer of isoleucine. Okay. So be able to answer like these multi-step questions. I think this was a pretty straightforward question in terms of like what you should do here. But it was a good review for what we did last class. And I think there was a question. Okay, so I had a quick question. I was able to watch your videos on YouTube about trigger movers and the others. Yeah, all the videos, first of all, the Enantiomer video is already up. That was the one from last week. And yes, this one will go up after, yes. Abby, will there be any other molecule besides C with chiral centers on the exam? Besides C? Abby, can you explain a little bit what you mean by that, besides C? Oh, besides carbon. Will there be any other molecules besides carbon? No. Yes, I told you that they do exist in the real world, like especially in inorganic chemistry, but you guys are only dealing with chiral centers with carbon atoms because that's organic. But yeah, great question. Good, yes. Is it wrong to include the hydrogens because they're stereochemistry arranged? Include the hydrogens where, Julia? Are you talking about when I drew them as the red hydrogens? Oh, yeah, so in terms of like proper like IUPAC rules, like drawing a wedge hydrogen here and here is not considered accurate. Like, do we really ever take points off? No. Like, I've never seen Dr. Pearson take points off for writing in hydrogens that aren't supposed to be there. Yes, it's not accurate, but no, you won't lose points or anything like that. Okay. Exactly, Abby, you like you said, we won't be drawing on the exam anyway. All right, let's jump in. I still don't have my printer working, so I guess I'm just gonna be writing everything down on paper, but we're just gonna jump into Fischer projections. I think you guys are pretty good at this point, or should be good with everything other than Fischer projections. And this is like another technique that I teach kind of differently than like most things, but whatever, take it with what you will. So we're on page 45 if you're following along in the student workbook, and I'm gonna do 7A. I know, I'm not feeling so great, as you can tell. So I thank you for catching that. I'm hoping that it's nothing. So just gonna think positive and manifest that energy, right? All right, so we're going to do 7A. So 7A is going to be something that looks like this. Okay, and honestly, like these may be intimidating, but I actually kind of like them. Then you guys will too by the end of this, I promise. So we're here. So what is a Fischer projection? And honestly, Fischer projections came from like the study of sugars and monosaccharides. Thank you guys, you guys are sweet. It came from this study on like, it was like sugars, like simple sugars. And since sugars have a lot of, chiral centers in them, I don't know if you guys know that, glucose, like the structure of glucose has a whole bunch of chiral hydroxyl, groups on them. And it's kind of similar to this. So Fischer projections was just a nice tool that arose from that study that was, helping us to really get stereochemistry right in the sense like since there's so much chiral centers in these molecules and these structures, this tool was used to really like keep track of like which center has what configuration, and that's why they kind of look a little intense. But okay, so in terms of we're gonna go both ways. We're gonna go from line angle to Fischer and then Fischer to line angle. So the first way how I would do this is it's always going to go from line angle to something that I call the Cis or flyover projection. These are my words, like, to the Fischer. Okay, so every time this is what you should do. Line angle, which we already have, to some sort of Cis flyover projection to some sort of Fischer. Okay, so this is actually pretty easy. And what you want to do is you, from this line angle that's already in the trans orientation, you want to rotate every other bond so that everything comes up on one face, or the Cis face, okay? So by that I mean, let me rotate this bond. Let me rotate the other bond. We're doing every opposite bond, okay? So that, and this might be very hard for you to visualize, and don't worry if you can't really see it, but just know that you have to rotate every other bond. So what happens to that? Well, you draw a long line, okay? And you write your end groups, okay? So essentially, my end groups are going to be the CH2OH group. That's this group, CH2OH. This is that one fragment. And then up top here is this aldehyde, okay? So that's the other group. And then you just draw one straight line connecting the two, okay? So what happens is that anything that was down, okay? So like this dashed hydroxyl or this wedge hydroxyl, it's going to be now upwards. So you're literally rotating it up. Remember that whole, let me see if I still have the model. No, but I can make you guys one real quick. Give me 1 sec. So I just want you guys to see this visual again. So if I'm talking about this hydroxyl group, let's say right here, it's the orange one, while the green would be like the hydrogen that's not drawn in. So if I'm going to rotate that bond upwards like this, 180 degrees, that orange, which was the hydroxyl dash, is now an orange hydroxyl wedge. You guys can see that? I'll do it one more time. So down, that orange, I'm talking about this chiral center, the black is this carbon, and then that orange is the dash hydroxyl. And if I were to rotate that bond 180 degrees upwards, it now sticks out as a wedge, okay? So that's a really important, like, I guess, find. So what does that tell me? Well, anything that's down is gonna just invert configuration, essentially. So that dashed hydroxyl now becomes the wedged hydroxyl. And anything that's already up, okay, anything that's already up stays, like is already in the upward fashion. So this hydroxyl is already up, so let me just keep it in the same wedge. This hydroxyl was rotated upwards, so I'm gonna remember to just draw that as now a dash. And then this one was already up, so keep it. Okay, so that's literally all I do. Okay, so that's the Cis flyover projection. Is anybody confused on how I got to that point? Okay, I think that's good. All right, so from there, you need to basically pretend that you're Superman or Superwoman, and you need to position your head at a specific site, either the left or the right side, such that your head is where the highest priority group is. Okay, so what does that mean? So out of the CH2OH group on my left, or the aldehyde group on my right, which one would be higher priority, okay? And the answer is it's going to be the aldehyde. So this clearly looks more complex. This double carbonyl bond is more complicated in terms of bonding than this CH2OH group. So essentially what you want to do is I want to fly over it like this. Okay, and I'm looking down, like I'm looking down, okay? But I mean by orientation, some people do it, you know, well, not down there. Some people do it like that, and they put their head here. Okay, and that's what you have to distinguish. Is it this way or is it this way? Okay, and it's pretty obvious, like, you just really look for the same thing. Yes, it's based on IUPAC. Yeah, I see. I have a couple questions. Charles, why does the line you drew on the left-hand side of the file? What is the line? Let me see. What does the line you drew represent on the left-hand side of the flyover projection? Oh, this? Oh, I'm just showing it's the end group. That's all I'm showing. Gotcha. So this is just showing that, oh, this was the CH2OH group at the end. Like that was this CH2OH group at the end. That's all I was saying. Yeah, and in terms of priority, in determining which side is more priority, it's just based on, you know, IUPAC again. So here you would have carbon to an oxygen versus carbon to a hydrogen. So clearly you can tell that this side is going to be higher priority. Okay, so now the next step is the Fischer. So you have to imagine now that you're actually, like, how you're viewing it is how this guy is coming down. Okay, so imagine that I had this whole, like, chain here. I'll do it again. One sec, I'm making a model for you guys. And trust me, we'll have plenty of time to review and everything like that, so don't worry. Okay, so essentially it's like this. Like, if it keeps going, imagine I just added 2 carbons here, but there could be more and more and more, keep going. So essentially, like, you guys are, like, viewing it like the way that you see it on the screen right now. Like, you are Superman, Superwoman, you're flying over this, and this is what you're looking at. So you have to basically imagine that you're looking at a whole bunch of V's. So by that, do you see what I mean by V's? According to this guy that's flying over, he sees a whole bunch of V's sticking out of the page. Does everybody see what I mean by V's? Like, okay. By V's, I mean, like, you're quite literally seeing, like, this. Something that's a dash and something that's a wedge. Like, I'm flying over, like, this is, like, I'll do it from a side view, maybe this helps you. My pen is like Superman, and the tip of the pen is going to be the head. So if I'm looking directly down, I see that, okay, these V's, okay? And on your Fischer projection, what you want to do is you want to translate it like that, okay? So what did we do? We went from this trans orientation, we rotated everything to this cis orientation, we're looking over it like this, and then we're going to transplant it like that. I know that might have been a lot, but I promise it's really not, okay? So then from there, you go to the Fischer. So you draw one vertical line. And if you guys are, like, confused, I'm telling you, I'll get you on examples, okay? So just bear with me. So you draw a line, and the thing that goes on top is the higher priority group, and the thing that goes on the bottom is the lower priority group. So we already said that this aldehyde is the higher priority group, so you can do one of two things. You can either draw in that aldehyde the way that you see it, or you could abbreviate it. And the abbreviation for aldehyde is C parenthesis O H. Okay, so you could have just wrote C parentheses O H, or drawn in an inline angle formula. Same thing with down below. We see that we have the CH2 group and then the hydroxyl group. Okay, so that's like the first thing. Now, however many chiral centers that there are, you have to draw horizontal lines. So there is 1, 2, 3, 4 chiral centers for a total of 1, 2, 3, 4 horizontal lines. Okay. So then, from this guy's perspective, this guy or this girl's perspective, looking downwards, anything that's on a dash, okay, you can see would probably appear on my left-hand side. So let me see if that makes sense to you guys. So for all intents and purposes, this is my structure, okay? And let's just say for carbon 1 and carbon 2, you see that the green is that hydrogen right here, and the other green is this hydroxyl, okay? So if I were to translate this up to here, do you see how those greens now appear on the left side? So it's this guy viewing it, the green. So the green, like I guess spheres are going to be the dashes, and the orange is going to be the wedges. And when you translate this onto the Fischer projection, you can see how the wedges become the right side, and the green becomes the left side, or the dashes become the left side. Okay. So I hope you guys saw that. So anything that's on a dash is going to appear on my left. So hydrogen, hydroxyl, hydrogen, hydrogen. So hydrogen, hydroxyl, hydrogen, hydrogen. Anything that's on a wedge appears on my right. So that would be hydroxyl, hydrogen, hydroxyl, hydroxyl. Okay, and that's it. Okay, so yes, people say you can memorize it. And the memory thing, I'll just say it anyway, is if you're flying over it left to right, like this, left to right, all dashes are always going to be on the left, all wedges are always going to be on the right. If you're flying over it from right to left, like the other way, all wedges are on your left and all dashes are on your right, okay? I don't think memory is, my memory is not long enough for that. So I just really see it, and I think that's pretty obvious. Let me check out some of these questions and see what you guys are saying. Brian, a way to remember, oh, well, there's some stuff above here, hold on. How, what's going on? I think we're here. Kelsey says, can you explain how you know what perspective to look at again? And it's based on what you did for, you know, assigning priority for the chiral centers. It's just looking at the atoms that are attached, and like basically both end groups, you have a carbon, and then the oxygen group was directly attached, okay, to that carbon, whereas on this carbon there were hydrogens that were attached to it. Okay, so that's why I already knew that this was an oxygen, which takes higher priority than the hydrogens that are at that position. How? The head of the person is towards the highest priority group. Yep, that's true. Maddie, it's based on the priority. Okay, you guys are all helping her out. That's awesome. Thank you, thank you, thank you. Awesome. Brian, the way to remember that is the wedges and dashes are on if the head is on the right. Yep, exactly. Yeah. So what Brian said is a great summary of literally what I just said. You can either remember it or you can just like see it. Like I think I pretty much see it. How can I know to put attached to a carbon? How can the middle two hydroxyls be chiral centers if they are both attached to a carbon? Hydroxyl. There are still 4 different substituents with respect to each of those carbons. I hope that makes sense. Abby, the bonds are different. Yep, there you go. John, because of, there you go. You guys got it. Yep, thank you. Okay, cool. So let's keep doing more. So that's 7A, 7B. So we have a less complicated one, but so we have this and we have that. Okay, and it doesn't matter which bonds you pick as long as it's every other ones. So that would be, you know, maybe let's just pick this one and let me pick that one. Okay, so that was the line angle. Then I need to go to the flyover. Okay, so the flyover is going to look something like this. So CH2, maybe, and you know, they come out every time I draw them. They come out differently. Like sometimes I draw it like that, sometimes I draw them up, like, but it doesn't really matter as long as you know you have this kind of straight line going on. And let's just say, actually, I should draw it this way. It doesn't matter, but it's better so that you can draw it for the flyover. So it looks like this now amino group, which was down, is now oriented upwards. Okay, sorry again. So if it goes up from the down position, which we saw already, so if it was down and I rotated it up, it now becomes the opposite configuration. So that would be the dash NH2. This bromine is already up, so I don't have to worry about that. And then we have the CH2, CH3 group right there. So this is my flyover, okay, or cis projection that I have. Then I need to decide, where do I put my head for flyover? Is it on the left side or is it on the right side? Well, clearly the hydroxyl is more important than the methyl group, so I'm going to draw it like this, and I'm looking down, okay? So from that perspective, okay, I'm going to draw this. This is making more sense with the visual. Good, I like that, okay? So I'm going to now draw the condensed form, so this would be a CH2OH at the top, and then CH3 at the bottom. So that's what I was talking about, these groups and that group. Okay, so CH2O3 is at the top. The highest priority is always at the top, and then the lowest one's at the bottom. So what you're doing now is, let's say my head is over here, that's this chiral center. Now watch this visual. You're flying over it like this. You have to translate it like that, okay? So now notice that all the wedges would become on the left, and all my dashes, which are the oranges, are going to be on my right, okay? So then there are two chiral centers, so that's two horizontal lines. We see that anything that's on wedges seems to appear on my left from this perspective, and then anything on my right appears to be like from the dashes. That's your answer. Okay, so let me go back to these chat box questions and see. Will we go over assigning priority? Right, yes, we will. Yeah, this is making more sense. I'm so happy, that's good. You only draw flyover chiral centers, right? So you ignore the carbon with two hydrogens. Exactly, that's great, Lauren. Annalise, is priority assigned by atomic number in this case? Yes, it is. Maddie, I was wondering the same thing. Is that CH2 representing the Fischer projection? No, that CH2 is not representing the Fischer projection. Again, the only thing that's horizontal are chiral centers. Anything else is extra. So like this extra CH2, oh, that's my fault. That's why you guys are confused. There you go. I am right, CH2. Yeah. Oh no, what am I doing? Did I do that right? Yes, that's right. Yeah, I'm sorry. I forgot the CH2 before. The first step of the rotating bonds secures me. Can I just move all of them to the top? Yes, Emily. Yes, you can. So yeah, a lot of people don't see that visual, and that's totally okay if you don't see how you rotate upwards. Just know that everything is going to be up top, and anything that was below or before, like this this wedged amino, is now a dashed amino up top. Yeah, so that's good. That's a good shortcut. I want the bottom group on the Fischer be the ethyl. Charles, oh, there you go. Yeah, I see you figured it out. Okay, so we're good. Sometimes I make mistakes. I'm going quick. I also don't feel the best, so I'm not as accurate today. 7C. All right, so 7C is weird, and I want to go over that for a reason. So 7C is actually kind of a trick that I didn't mean to do when I was writing this book, but Dr. Peterson was very happy that I did it because she was like, I teach that anyway, like sometimes. So I think that we had that. And here's like what I'm going to talk about. So this is something that we haven't talked about with chirality yet either. So, okay, here we are. So typically, what you would do exactly what we've been doing is we would rotate every other bond, draw that cis flyover projection, and then draw the Fischer projection. But what's happening here is that the end groups are not in the right orientation. And what do I mean by that? Well, clearly the ketone on the left is the highest priority group on the left, the end group. But on the right, it's not a methyl, it's going to be the ethyl group. Do you guys see that? The ethyl group is clearly more complex and higher priority than a methyl group. So what you can do is you can rotate around this bond such that you get this ethyl in plane. Okay, so I want to get this wedged ethyl to be in plane. Okay, and I know like you're like, oh my God, that's like the worst. And there's this thing that, that I kind of teach, and it's called WPD. Okay, so like, have you ever heard of like, Gainesville Police Department? It's like GPD, or like Los Angeles Police Department, LAPD. Like, so just think like, make something up like W Police Department. I don't know. And basically, damn, I like that. Damn, what's poppin', Brian? You always got something. That's funny. I like that. So you guys all know that. So I don't know. For me, it's WPD. And essentially, what you need to know is doing one rotation, you move to each consecutive letter. And if that doesn't make sense, I'll catch you. So watch this. So this wedge, okay, from one rotation is going to go to the plane. And then this plane methyl group from one rotation is going to become a dash. And then whatever that dash was is going to become a wedge. Okay, do you see that from one rotation? So essentially, that would look like this. The result of one little rotation around that bond gets, so that wedged ethyl group is now planar ethyl. Okay, so that's, I'm going to draw it in blue. So this blue group is now here, okay? This planar methyl group is now a dash. So that planar methyl group, which is red, is now a dash. And then that dash, I need another color, hold on. And this dashed hydrogen, which was a dash, is now a wedged hydrogen. Okay? And then you're going to spill in everything else like it was. Okay? And that only affects that chiral center, obviously. But you see what I did there? So I rotated, and this is something we haven't had to do before, but it could come up on your exam, is making sure that that end group is in fact really the best possible end group that it could be. And in this orientation, it was only a methyl, and it became an ethyl here, okay, from that. So I did it in the plane, is that wrong? I did it plane to wedge to dash in the circle. No, that's okay. That's just as if you would be rotating it backwards. That's okay as well. And so what situation would you use that? I'll explain that one more time. If the ethyl group had been on a dash, would the methyl group become a wedge? If the ethyl group was on a dash, would the methyl group come on a wedge? No. Well, it depends on which way you're going around. So like, if you're saying, if the ethyl group had been on a dash up here, then that dash becomes the wedge. And then that means that the methyl group, which was planar, became still a dash. It just depends. And then, so when would we need to do that? So in all the other instances that we did, if you looked, like there was just 2 hydrogens here. Like there isn't anything that's going to change this end group. There's 2 hydrogens here. Like it was a very obvious, like, it was a very obvious thing here that like, this is a CH3 group at the end, but like you could rotate it and have the ethyl group be at the end. Like that's kind of all I really have for that. Isn't that a sec-butyl? What's sec-butyl? Emily, yes, this could be sec-butyl. I see that. Yeah, that could be sec-butyl. If it became a dash, I would, this is sec-butyl, by the way. If it became a dash, I think the method would become a wedge. I'm confused on all these hypotheticals, honestly. Let me just keep doing more, and I'll get you guys. So anyway, so we're here. And what we need to do is rotate every other bond. So now I'm going to rotate these to get these up. And the orientation I want that is going to turn into this. So, so here's the ketone, here's the ethyl group. So this chlorine is already up, so I can leave it up like this. This hydroxyl group is down, so going up, remember to flip that, whatever it was. This dash is already up, okay, and then we're there. Okay, so now put your head so that you're flying up here. You're gonna look down, okay? Again, for this situation, my wedges are the green spheres and the dashes are the orange spheres, and I had to translate it like that onto paper. So that would be, this is going to be my, that ketone up top. This is gonna be my CH2, I'll just draw it out, CH3. I have 3 chiral centers. There's a chlorine, hydroxyl, hydrogen, 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 CH3. Okay. Kelsey, if it became dash, I think the methyl would become a wedge. Okay, I'm really confused. I don't know if I said something wrong to you guys, because everybody seems to be saying something about this. Like, can somebody like speak it to me? Because I'm kind of confused when you guys type it. Are you guys confused on the WPD thing? Oh, I can't hear you at all. I think you're pretty muffled unless it's just me. Anybody hear her? Anybody hear anybody? I don't hear anyone.
I don't hear her.
Oh, okay, cool. Anyway, I can just try and re-explain this WPD thing one more time. Like, the only reason, like, this is like the only example I think in the student workbook that it has this specific case. So don't worry about it in terms of the other things. But I literally wrote a star next to it because sometimes, like, if this end group isn't in the like highest priority, meaning this ethyl, you can rotate, just a little bit just to make sure that you get that ethyl in plane. And to do that, to keep your stereochemistry all aligned without visualizing it, is this, like what's poppin' thing that Brian said, or, like something police department, whatever you guys want to do. And one rotation causes this wedge to go in plane. And even if it, let's say this was on a dash, you could rotate it twice, okay? So just say you're gonna do 2 rotations and move everything 2 rotations over. I think that's kind of what people are saying, especially Kelsey at the bottom. Like you're saying is, maybe, what if I had that same structure, but this was a dash? Could I still do the same thing maybe? I think that's kind of the big confusion. And yeah, you're still gonna rotate around that bond, but I need to get to plane. So maybe I'm gonna do wedge plane, so 2 rotations. So that dash goes to plane. Sure, I can do that, but that's 2 things. So this plane thing, is gonna move 2 things over, and that becomes the wedge. So does that make more sense? Okay, cool. You can do more than 1 move at a time, just as long as you're consistent across the board. Oh, perfect. Okay, cool. Yeah, you're good, you're good, you're good. Right to left means from that. Right to left means from. Right to left means from feet to head, yes. So wedges on the left, yes. Why does it need to be in plane? That's just based on convention for making this structure. Okay, that's just convention. Like longest chain. Yeah. Why do we want it at the end? Convention again. I'll just give you guys that. It's the highest at the top. If the highest at the top. Why do we want what at the end? What do you want at the end? I'm confused. That's just priority. It's just like you guys name like the ketone carbonyl up top, and that's like the highest priority group, and then always the lowest priority group with respect to the end groups. Like it's just like out of the end group on the top and the end group on the bottom, the highest one goes on top and the highest one goes on the bottom, and there's no reason for that. That's just convention. Oh, I see. Well, thank you, Abby. I didn't understand what you guys were asking. You guys were asking about why does it have to be an ethyl, not a methyl? It's ethyl because the convention for the IUPAC people say that in the Fischer projection, this vertical line has to reflect the longest carbon chain. Okay, I didn't get what you were asking. Sorry about that. So this vertical line has to reflect just the long parent chain, and then anything horizontal is the substituents coming off. So yeah. Okay. There you go. Yeah, I didn't understand the question. All right, so that's that. And let's just do one more example, and then we'll go the other way, and then we have to move on to, doing our summary practice, so 7D. So we have, maybe this. This is pretty complicated, but just because of how many things are going on, but nothing that you guys can't do. So here we go. And the amino. Okay. So I don't know, I'm just gonna decide to rotate this one and rotate that one and see what happens. So essentially that's gonna go to a structure. Oops, I keep rotating you guys. So that's gonna be something that looks like, and these don't have to be like so accurate, they just need to like have this kind of cis orientation. And essentially like this thing was down and now it's up, so it must be a wedged sulfhydryl. That was already a dash, so we can keep it up. And then this amino group was a wedge, so then it moves up as a dash. Okay. Out of the flyover options, is the carboxylic acid higher priority than the aldehyde? Yeah, we have extra hydroxyl stuff going on. So I'm going to do it like this and look down. Okay. So then I draw one vertical line. I'm going to draw my carboxylic acid at the top because that's the higher priority. And then I'm going to draw the aldehyde, COH, at the bottom. How many chiral centers were there? There were 3. 1, 2, 3. Okay, from this perspective, the dashes, okay, are the orange spheres and the wedges are the green spheres. And translating that shows me that my dashes are all going to go on the left. Okay, and you guys should start being able to see that without me using the model. But that would be hydrogen, hydrogen, sulfhydryl. And that's how you do these. Okay? I think it's enough practice for these. They're not too bad once you see how I do them. Can you quickly go explain the priority for 7G and 7H? Yeah. Yes, of course. In terms of determining which end group is higher priority for these two guys, what you're looking at is the aldehyde here, or this ester. ET stands for ethyl, so essentially it's that. Okay, and Me stands for methyl. Okay, and it's based on complexity again. So like you have you have both of these carbonyls, so those are pretty much the same. And then directly attached, you have a hydrogen or an oxygen. So clearly higher than that one. And same thing over here. They both have these same carbonyls, but this has an oxygen and this has a chlorine. Chlorine is higher atomic number, 1, 2. Does that make sense? So you want to have your heads here and here. Okay. Hope that makes sense.
Excuse me, but
yeah.
I think in 7H, the methyl group, the MEO was actually the first. Yeah. In the workbook. Yeah, 7H. It wasn't the chlorine that was first. It was the methyl with the O that was first in the workbook.
This was labeled number 1 in the workbook? Yeah.
Yeah.
I don't like that. I think it's a mistake, honestly. That could just be a mistake. Yeah, the acid chloride, like this is clearly the highest priority. This has to be the right thing. Because chlorine is higher than that. Yeah, you guys are all seeing that. You guys all know that, right? Chlorine has a higher atomic number. It could just really be a key error if that's really what it is. Yeah. Okay. Does that answer? Oh yeah, cool. Okay, good. All right, so let's move on to the opposite way. So this is a little bit more challenging for people. Okay, and then we'll move on to a review questions and stuff. So we're on page 46, and we're going to do 8A. So on 8A, we have now a Fischer projection. Okay, and something that you guys should know, and it's like this weird structure, is this. Oops, sorry about that. Is that we have, and I'm sure Dr. Peterson, if she taught this portion of your class, did this, because I remember this very vividly. Okay, so like this is basically equivalent to what I'm looking at right now with the 2 chiral centers. And what you have to imagine is that these end groups are oriented away, like down. So like, and how can I prove that to you? That would be like, here, I'm drawing this model because I think it's very visual. It's important that you guys see these. Is that, so like right now this would be like the Fischer projection, right? Okay, so hopefully you guys can see all that. This would be like the Fischer projection. And you guys can't see because I just like hid those. These blue spheres are these end groups. That's the CH2OH at the top and the bottom, and that's why they're oriented as dashes. Do you see that? They're going down into the board. While these chiral substituents, these hydrogens, these hydroxyls, are the orange and the greens respectively, and they're both coming out like the wedges are coming out towards the camera. Okay, so that basically is kind of showing you the stereochemistry of like what I'm looking at in this Fischer projection. Okay, so we're basically going from this to the flyover like this, and then we're going to rotate back to normal line angle like that. Okay, so one more time. So we're going to go from the Fischer projection that we're looking at on the board to the cis flyover that we're used to, and then rotate back to the line angle. Okay, so how do I do that? So I'll get your questions in a sec. Essentially what you want to do is you draw this cis projection. So I literally would just draw that, okay, always. And the CH2OHs refer to that and that. So that's the CH2OHs on both ends. Those are my end groups. And then I would just pick which side. It doesn't matter because they both have the same end group in this situation. But let's just say I'm going to put my head here, and I'm looking down. Okay, so if I'm looking down, from this perspective, it basically means that, and I draw this every time and people laugh, like, because I'm like not good at drawing, but this is like the back of the head of someone. Like this is as if like someone is literally like facing down, like directly on top of this. Okay, like imagine like you like are belly flopping on top of this, basically. Okay, so your left hand, okay, my left hand is these hydrogens, and my right hand are these hydroxyls. So now I'm going to turn and fly over. So this is my left hand with these hydrogens, and I'm turning and I'm flying over. So they would all have to be that. Do you guys see this? And maybe I'll try and demonstrate it with the model. These hydrogens are these oranges, and if I'm looking at it like this, the way that it's depicted, I'm gonna fly over like this. Get ready, watch. The orange spheres we're following. We're flying over, and then this is now corresponding to my cis flyover. Do you see that? So we went from these orange spheres on my left from the Fischer projection to the cis flyover right now, and that's why they're on wedges. And then now you just rotate every other bond to get back to the transline angle, and you'll see that you get. So what I do here is count carbons. So there's 1, 2, 3, 4. Oops, this should have been on this position, but 1, 2, 3, 4. So it's 1, 2, 3, 4. And then you can just fill it in the patterning based on what you see. So that was up, still oriented up. This is now oriented down, so that becomes wedge, and that's the CH2OH. And this is how you go there. Okay, so yeah, definitely a little bit more complicated going backwards, but I think it's like pretty much the same thing. Like you have to visualize it like this, like belly flopping on top of it. Then you fly over it, and then once you have that cis conformer, you just rotate every other bond back down. Okay, here we go. Let me go. Oh, there's a lot of questions. Here we go. The priority, yes, is based on the functional group, or it's both. The priority is based on the functional group, which is dependent on the atoms that are involved. So by proxy, you're saying it's also the atomic number. That's the same thing. Same functional group and atomic number is basically saying the same thing in that situation. Charles, to clarify for priorities, top group. Okay, you know what? We're going to do this. Let me do like R. Let me do do you guys follow that trend? This is priority, okay? From highest to low. And you can just see like what's changing is like all this is consistent. So that's not going to help me determine anything. But chlorine is higher atomic number than an oxygen. And then this oxygen is better than this one because this one has more carbons attached while this one has hydrogens attached. And this one doesn't even have that oxygen. So you can see like in terms of like what's attached, you can kind of dictate that priority. And then there's more and more and more going down, like in even other types of things, like other types of atoms. Okay, so Charles, hopefully that answers your question. Kelsey, why are the carbons connected with a dash? Kelsey, what are you referring to?
Hey, Stephen, I think she's asking the same question as Julia beneath it.
Oh, I see.
Yeah.
This? Yeah, you're right. I probably should have just made that straight. That's good. Yeah. Thanks for catching that, guys. It's hard to understand what you guys are saying, like when I'm reading them backwards and like reading them back after we talked about it. But yeah, so you can tell, like, just looking back at this again, the, sorry, I'm out of breath. Sorry. These blue spheres are going down. These orange and green ones are coming up, and then this is just plain. So that's why it's a straight line. Okay. All right. Why is not attached to 2C's? I think atomic number is part of the complexity. Okay, and Mary, I think atomic number is priority, then complexity. They're kind of like one and the same. I do both at the same time. Like I immediately first, like macroscopically, look at complexity, and then I quickly look at then I look a little bit further at the identity of the atoms, which is priority essentially. And what is this file? Let me get back to you on that. I want to just do like some of these review questions real quick, and then we can move on. Okay, so I think that's enough practice for like Fischers and stuff. Hopefully you guys can just practice a little of those over the next few days. If you guys don't feel great, I want to do some, critical thinking questions. So if you're following along, we're on page 48. Okay, and we're going to do that isoleucine critical thinking question because these are important. You guys should really know these. Okay, so I am going to give you guys a second to pull that up. I'm going to share my screen and we'll get started, okay? I'm sorry, I'm not really my best today. I'm not really feeling my best, so I'm just trying to help you guys out as best I can. So we are on this chapter. Sorry guys, 1 second. Chapter. And here we are, finally found it. Okay, so I'm gonna share my screen with you guys and we'll talk about this. Share screen. Okay, so hopefully you guys can all see this. This is, you know, what we're looking at in the student workbook by Avicia. Okay. Oh, thanks guys. I'm just saying that. You guys are sweet. Oh, you guys. Okay, so let's just kind of go through these critical thinking questions. So isoleucine. So we kind of did this in the beginning, and the first thing you want to do is circle all the chiral centers. So for me, that's pretty easy. I see I have this center right here. We have the ethyl group to the left, this whole right fragment, I don't even know what to call it, that methyl group up, and then the hydrogen that's on a wedge that we can't really see, okay? Then the next thing is going to be this amino group that we already saw. That's the amino down, the carboxylic acid to the right, this whole left alkyl chain, and then the hydrogen on a dash, okay? So those would be like the two chiral centers that I see, okay? So let's assign absolute configuration to these things, okay? So maybe I can change colors. Oh, I can, that's cool. Okay, so I'm talking about this first, you know, one all the way to the left. And again, we see that we have this whole right chain with nitrogens and oxygens and stuff. So that would definitely be number 1 to the right, okay? This ethyl group is definitely gonna be number 2 over here. This methyl group is definitely number 3 up top, okay? So if I were tracing that, it would be 1, 2, 3. Do you follow my pen? 1, 2, 3. And tracing that, that is gonna be clearly the R configuration, okay? But is that 4th priority group oriented away? And no, it's not. So remember that you can either just visualize it as if you were behind the screen, or you can just remember to flip that letter. So if it was R, it's really S. Okay, so it would be S for that one. Okay, let me change this one to another color. So we're going to be over here again. So you guys should see we have the amino, which is 1 because the nitrogen is directly attached. Okay, so let me change color here. Okay, let me get my pen. So this would clearly be 1. This would clearly be 2 because of the oxygens that are close by. And then this thing would be 3. Okay, so tracing that, you get S. Okay, counterclockwise. Okay, and you also get S. So both of these chiral centers are actually the S configuration. Okay, so that's part A and part B.
Wait, could you explain what 1 is again for that one?
What priority number 1 is for this chiral center?
Yeah.
Yeah, so that would be the amino group. So I'm looking directly attached. You see that, the nitrogen?
Yeah.
Cool, okay. So see, draw the enantiomer of isoleucine. Okay, so that's really easy. That would be like drawing the exact same thing. Let me see, can you still see my paper as well, like while you have my screen shared? Yes? Oh, awesome. Okay, I didn't know that. So essentially, all you want to do is draw that same exact structure. I know you could see both of these things. That's cool. And I did the exact opposite of what I wanted to do. You draw your skeletal structure, and what you do is you just change your shading, either wedge to dash or dash to wedge, of your, you know, chiral center. So that would definitely be the enantiomer for part C. Okay, the next thing that you will see is that the plane of polarized light rotates alpha. What the hell is alpha? So alpha basically just means that, like, or we didn't really talk about this like in terms of theory, but what chiral centers do is that they rotate light, and they rotate them different degrees to, you know, left or to the right. Okay, so we use plus to indicate towards the right, we use negative to indicate towards the left, and whatever the magnitudes are, like, is kind of irrelevant. You just have to know that, like, the sign is going to change with enantiomers, and that should make sense because, you know, this specific configuration that we're seeing on screen, maybe the one that's depicted, that's going to rotate it, let's say, plus 2.1 degrees towards the right. But if I were to invert all of those centers, then the exact same magnitude is going to happen, like 2.1 degrees, but now the opposite direction because you have the opposite kind of chirality of it. So really what you want to say is if I'm predicting the value of alpha, alpha is really just negative 2.1. Okay, it's like stupid, you know, does that make sense? Like, it's just the opposite of whatever the number is. There's no way that you guys know how to calculate alpha. Like, yes, there's a formula that exists in the world, but in terms of your class, you guys don't cover that. Okay. D, draw the Newman projection based on the line of sight. So you see how we're like kind of building. So if I'm looking down, you know, this bond axis right here, my first carbon, so this is part D, my first carbon is going to be this CH2, CH3 group going down. We're going to have this CH3 group going to my left. And then we have this hydrogen going right here to my right. Okay, so I think that's kind of obvious based on that arrow that I first drew for the first carbon. Then on the back carbon, you have that carboxylic acid going directly up. Okay. You have the amino group coming down to my right, that's NH2. And then you have that hydrogen coming to your left. This is definitely going to be the Newman projection, okay? And then E, provide the proper name for this Newman projection. Okay, so on the front carbon, the biggest group is clearly it looks like this ethyl group. Let me just circle that. The front carbon, the ethyl group is the largest. And on the back carbon, the carboxylic acid is clearly the largest. So in our specific, Newman, we see that we have these groups, those two largest groups. So this is clearly going to be called the anti-conformation. Okay. F, draw the Fischer projection of isoleucine. Okay, so we did E, now we're on F, so that was E, and now F. I don't know if you guys can all see this. So F, so we're drawing the Fischer projection of how it was depicted. And essentially we're going to start from line angle, like we are used to. So NH2. We have that. And I'm going to rotate every other bond, okay, to get this cis projection. Okay, so this dash is already up, so that forces this amino group up. Okay, so we're here. I fly over it like that. I look down. I draw my vertical line. This is my highest priority group at the top. Okay, this is my lower priority group at the bottom. I have two chiral centers. Those dashes are to my left, so that would be here, and here, and here, and here. And that's how I would do this question, all right? So this question, number 10, sums up everything that you should know for this exam, okay? That's why I think this is a really good question to cover. So knowing what a chiral center is, knowing how to synapse configuration, knowing what an enantiomer is, knowing what chiral centers do, meaning rotating light, knowing what a Newman projection is, knowing the names of Newman projections, and also knowing Fischer projections, okay? So I feel like that's pretty much, if you got this question if you thought this question was easy, then you guys are chilling for your test, okay? Really. All right, let's keep going. So let's clear this. Clear all drawings. I'm gonna move on. Let me see, I think I have some questions going on. What would you do if you were to ask about alpha for a diastereomer? You don't know enough knowledge about that, Jada. So yeah, you're not going to be asked that. Sabrina, unless your answers were drawn flips like a pancake without changing the dashes and wedges would both be correct. Unless your answers were drawn flips like a pancake without changing dashes and wedges would both be, yes, that is true. So, how did you know how to output? So I know how to pick the front and the back carbon based on this arrow that was provided. So it tells me that where that tip of the arrow is, that's the front carbon. And then what's beyond that, where this amino group is clearly the back carbon. Yep, and you guys all did that. Okay, yep. Can you explain the alpha thing again? Sure. So we didn't really talk about this, but there's something called a polarimeter. And here, polarimeter. And I think Dr. Peterson touches on this and here, so I'm sharing this with you guys. So this is a polarimeter, and in this chamber, in chamber 5, like we're gonna put a mixture of that solvent, of that solution that you guys have. So it's gonna have, like, let's say that isoleucine there dissolved in some sort of aqueous state. And what it is you can tell, like right now it's unpolarized. Like from this light bulb, it goes in all these different directions. That's what these arrows are indicating. But we put it through this filter so that we get only one type of direction of light. So notice it's unidirectional, it's all just going up. And when that light, which is now one direction, goes through this channel which contains that analyte, look how it rotates a little bit. And this is the end product. Notice that was before, this is it coming out, and this is what we see. That's the angle that it's rotated, okay? So one enantiomer of isoleucine is going to rotate it towards the left, like this. And then the other enantiomer of isoleucine is going to rotate it towards the right, like, or the other structure, okay? So that's kind of what alpha is. And you can see another example right here is like, you get one direction, you throw it through a sample of chiral analyte, and it rotates it. And that's basically what optical activity is. And that's with all these chiral stuff, okay? I think that is good for you guys. Is that helpful?
Yes, thank you.
Cool. Will you be testing optimal? Probably. Could you number 11 total Fischer 38 special conformance of good time? Yes, Lauren, I can. How did you guys know the Fischer projection? I just pick every other one. You can pick anyone. Like, I just knew that it's typically the one that contains something that is down. You want to like orient it up. And let me just keep moving. Okay, so I'm running out of time here. I might go a little bit over, but that's okay. So Zoom, share screen, go back to student workbook. So let's move on to this. This is really important. Okay, knowing these relationships. Okay, so essentially, you are going to have a whole bunch of these on the test, guaranteed, and you need to be able to determine the differences between the two of them. So essentially, what am I looking at here? So I have these aldehydes up top, aldehydes below down here, and it looks like they're mirror images. Okay. Somebody in the chat box tell me what they think the relationship is with these. And take a stab at it, somebody. Okay, okay, okay. All right. So we are torn here. So a lot of people are saying identical and a lot of people are saying enantiomers. And the correct answer is identical, okay? So you're right to initially think that it is a non-superimposable mirror image, right? But the problem is that if you see that they have the same end groups, what's happening is that, can you see my hands? Like basically they're just rotating it. They're taking the top thing, bringing it down, and bringing the down thing, bringing it up. So if I were to like, here, let me draw in here. If I were to basically show you this, draw, they're basically doing that. They're rotating. So they're basically zoop, like doing that. And then then you can see it's the exact same thing. Okay? So these are
Steven,
actually, yep.
I see that, but when you if you just say you do the line formula, so the H is on a dash on the left one, and then the H is on a wedge on the right one, and like all of them are like that. And so each chiral center, it went from dash to wedge, basically. Is that the definition of enantiomers?
Yeah, yeah, that could be one definition of an enantiomer, saying that wedges go to dashes and dashes go to wedges. Yeah, that could be one. And in this case, that's not happening because they're all still wedges. Remember that picture we were showing with like the bow tie, like, you know, we had this. So they're still wedges, even if I like were to rotate this like up and down like that. You see what I'm saying? So you're not really changing configuration, you're just rotating. That's why this is identical. Yeah.
Okay, thank you.
Yeah. 13. Okay, so 13, let's pancake flip that guy. Okay. Pancake flip it over, and you definitely invert all of your chiral centers. This is a mirror image. It's not superimposable. So what are we thinking for 13? In the chat box, guys. Yep, we're thinking enantiomers, Hal, yep, I see all these coming in, yep. Enantiomers is right. Okay, so this would be I, this would be E. Okay, cool. 14, okay, I see kind of like these mirror images, and also they are not mirror images because of this dash here, and they are also not superimposable. So these would be the definition of a chat box diastereomer, okay. But specifically geometric. I love that. You guys are catching it. So yes, it's not wrong to say diastereomer, but as long as you also mention that they're geometric. So they're geometric because these two substituents are differing on the face of the ring. They're both cis in this orientation, and they're both trans in this orientation. So yeah, so you can definitely say diastereomer, but make sure you also mention that it's geometric. And if it says to be as specific as possible, you have to mention geometric. Okay. So then over here, we see that we have, it looks like a bromine with, everything just kind of looks different. So what do we think this is for 15, guys? What do we think? Yep, love that. Constitutional. So this is just the same exact structure, same exact molecule, but they just differ in connectivity. So they have the same molecular formula, but they differ in, look how that hydroxyl is up here, and the hydroxyl was over here. So it's clearly just being moved around. So it should be C for constitutional isomers. So constitutional, okay? So then 16, so again, this is the hardest thing for people on this test, is using all their knowledge together to be able to like find these relationships. But this is definitely a huge skill to know. So basically, paper. So 16. So if you're given either a Newman or a line angle, it's a good idea to convert that Newman to obviously line angle. So I'm going to do that real quick. So that Newman should be something that looks like that. And we have, and then we also have that. So we are looking at that structure, and we want to, it looks like, rotate. You can now rotate this down. So it's 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Actually, you know what I could do? Watch this. Okay, so you see that? So we're basically here. I just literally turned this upside down, and I saw that this is where we were at. Okay, if I pancake flip that over, it becomes that. What do we think the relationship is with this structure to that one? Chat box, sit up if you can. What do we think 16 is? I see enantiomer, but it's diastereomer, guys. It's diastereomer. So how do I know that this is diastereomer? Like, if you were to draw that Newman projection in the way that it was, which is what we did, and then I flipped it, okay? Like, I mean, I literally just turned it upside down. Like, this is the Newman projection. I turned it upside down and then pancake flipped it. And I saw that this was going to be diastereomer. And this is a not geometric example, because I remember I told you geometric is reserved specifically for double bonds. So like this versus that. And it's also reserved for only these ring systems with 2 substituents, okay? Those are the 2 times that we can use geometric, okay? But this would just be diastereomer. 17. So these are difficult. So in 17, these look like these are chairs, okay? So how do I draw? We never really practiced this, going from chair conformer back to planar depiction. And again, if I call that 1 and I call that 4, you guys can hopefully use your trend. In this one, if 1 is going up, I mean, if 1 is being pulled up in this first chair conformer over here, and I want methyl to be equatorial, you know you would have to make that on a dash, correct? You guys all kind of follow that? Then on 4 we know is pulled down, and if we want that to be on an axial position, it also has to be down like that, okay? And then 5, okay, would have to be up. So if I want 5 to be up, I would want that to be a wedged methyl. Okay, so that's this structure. That's for the first one. Then if I did this for the second one, for 1 and 4, if 1 is down, and I want 1 to be down at that position, it's methyl. And then 2, 3, 4, if I want that equatorial, it should be, oh, was that 3? I'm sorry, I'm looking at the wrong carbon. So on 3, 1, 2, 3, we have equatorial. So that would be down, up, down. So that would need to be a wedged methyl group right there. And then 4 to be equatorial cyano would have to be dash. Okay, so this is the structure that we're looking at, okay? So you can see when I converted both of those to the planar depiction, they both have these, you know, mirror image structures. And then, can you explain it slower? Yes, let's see what the issue is here. Oops. I can't view the chat box for some reason. Let's see. Can you explain it before Newman line angle? And oh, you're talking about the other one. Okay, so I'll go back to that after. So here, what's happening is that we can clearly see that these are like the same thing. However, like everything has been moved over. So these are conformational isomers. Okay, so these are conformational isomers. Because you can tell that both chair conformers gave us the exact same structure. These are mirror images of one another. However, like all that's changing is that they were ring flips. These are conformers of one another. Because this is the same as if I would have done it 1, 2, 3, 4. 1, 2, 3, 4. Like you can number it whichever way you want, and you get the same exact stereochemistry of the numbering. So these are the exact same things, except in these pictures they are conformational isomers of one another. Okay, but conformational isomers can give rise to a specific type of, does that make sense? Wait, what is Lauren saying? Yeah, Caroline, I was just basically saying that. And Lauren, so if you flip a line angle, you have to change wedge dashes. Okay, yeah. So these are like conformers clearly because of the ring flip that's going on here. But what I was going to say is like the final thing is how to know, like, is it like just the conformational one, or is there something else going on here? Like clearly I know there's a ring flip going on, right? Like that's why these structures look different. So that's why I'm thinking conformational. But the reason why it's an enantiomer is because you can tell if I were to flip this over, so this is a mirror image and it's not superimposable. And yes, I was just going to say assign R and S, and you can see that all of these R's and S's are going to invert. Okay, but yeah, very good point. So these would be enantiomers. Okay, so at first they look like conformers. That's what I was kind of trying to prove, is that they look like conformers, but they're enantiomers. Because if you were to assign R and S to each one of these, they're different. They all flip. So the R's maybe, like, I'm arbitrarily calling them R, like, and even though they may not be, all of those would go to that. What's going on here? Why wouldn't it be identical? Can you rotate the molecule to superimpose them or that? No, it can't be identical because how do you flip them? Superimpose them or that will change the dash. Exactly, it changes the dashes to the wedges and vice versa. So like flipping this makes all of these substituents the opposite stereochemistry of your original. So that's why they're not the same.
So when you flip, you don't change the wedges to dashes, but when you rotate, you do.
No, you do. So like if you're like, let's say I'm pancaking flipping this one, it would become this. So this is what we're comparing to that. Do you see? And how every single chiral center flips its configuration. I hope that makes sense.
Sure. And that, I would say those are enantiomers, but so, and they're conformational.
No. They're sorry. I think I'm like confusing here. Yes, they are enantiomers. I meant to cross this out. I didn't write enantiomer yet. They are enantiomers. If I'm confusing people, these are enantiomers. I was just saying that in the beginning, my first instinct was to think that these were conformational isomers. I thought they were conformational because I clearly am looking at a ring flip. It looks like a ring flip. Okay. But when I went backwards and drew these planar depictions, I saw that they really are just enantiomers of each other, because you can either assign R and S or just, pancake flip it and see that all the signs changed. All the stereochems changed, basically. Okay. So yeah, that's basically that. I think that's pretty much it for your exam material. We pretty much covered everything. Let me see if there's anything else worth going through real quick. So again, this is really important. We talked about how to calculate. I'm not going to run you through this, but I'll just tell you how to do this. You would basically draw the Newman of the current projection. You would have to draw the next Newman of the highest conformer, which is the eclipsed one, draw the Newman of the lowest conformer, which is the staggered one, anti-conformation, and then calculate those delta G values based on this table, and subtract the highest one from the lowest one, and then that would be your torsional energy. So definitely a good skill to know. Practice this definitely when you can. This is a great question we wrote. I would also know how to do this one. This one seems like it's very similar to isoleucine. So make sure if you get this one 100%, actually let's just talk about E real quick. If a 50-50 mixture of this structure and its enantiomer that we drew from another step were placed in a polarimeter, what would alpha be? Okay, so let's think about that. So if they're saying that if 50% of the solution is this enantiomer, which rotates light one way, and then the other 50% is the other enantiomer, which rotates light the other way, what's going to be the alpha value in the polarimeter? Put it in the chat box. Let's see. All right, I got one person. 0, 0, 0. Yeah, cancels. Perfect. You guys got that. So that makes sense. So like, let's say the R is going to rotate that way. The S is going to rotate that way. So if you were to do that same vector thing we've been doing, head to tail, they cancel out. Or that's not right. Yeah. So like, let's say light goes in this way. Okay. And then there's R and S. And then the right sample rotates it that way. The S sample rotates it that way. And then when you put those together, you come out with the same exact thing. Okay, so in other words, they cancel each other out. So alpha equals 0 because the original light didn't change at all. Okay? No, we would never give you 75 to 25. We're not that mean. It's just conceptually. Well, but you could, maybe there would be like a question, like even if we didn't give you values to calculate, you could know that it would be skewed to whatever is more 75%. So like, let's just say like they tell you that it's 75% the R enantiomer, and you know that the R enantiomer is plus, like, let's say 2. So you would know that the number, that value would be skewed more towards, you know, whatever is more present in solution. And yes, that is true, John. All racemic mixtures have optical activities of 0. Yes, that's important to know. Okay, and with that, I think that's enough practice with you guys. 14 is just another relationship question. 15, same thing. And then that's it. So email me if you guys have any questions. Good luck. I'll see you guys.